strange looking result here. I guess strange is in the eyes of the beholder, but we're assuming that if n leaves a remainder of 6 when divided by 10, that it enjoys this property right here. It's divisible by 11 when you raise 2 to the n, add 2. That's actually divisible by 11. But anyway, let's write down what this congruent statement means. It means n leaves a remainder of 6 when divided by 10. And so you can rewrite that as 10m plus 6. All right, and of course, y'all, m is just some integer, right? M is just some integer, positive or negative, or even 0, okay? Because 6 is congruent to itself. Now, we're actually trying to show that 2 to the n plus 2, if n is in this form, is divisible by 11. That's what this means. Another way of restating this would be to say that 2 to the n plus 2, and again, there's 2 or 3 ways to formulate congruences, but if you take 2 to the n plus 2 and divide it by 11, that means it's going to be a proud member of the natural numbers, folks. And y'all have seen this capital N. It stands for all the natural numbers. Those are the positive integers. So like what I mean by that is just 1, 2, 3 ad infinitum. Okay, we'll just put the dot, 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 dot like that, okay? So that's what's going on with the givens. Now let's see how quickly we can get this thing proven, because it took me a while to figure out the main idea. Now you can see where this very first statement comes from. This would be 2 to the 6th right here. Okay, and by laws of exponents, you're going to get this result. In other words, we literally replaced n. We replaced n with this expression we wrote down right here. Then we used laws of exponents, right? Okay, this would be 2 to the 6 times 2 to the 10 to the 2 to the 10m. And so you remember how you can add exponents, 10m plus 6. So, or is this part right here straightforward? Now notice that 64 is actually congruent to 9 mod 11. Let me write that. 64 is congruent to 9. And of course, we're talking mod 11. Congruent to 9. Okay, and that's why we can replace this 64 with this 9. You see, we're getting close to home here. Look, we got a 2 and a 9. That's 11, right? But then we have the rest of this, all right? So in other words, that's why we could take this step right here. Now, the very next step is what's really fun. And it took me a while to realize that there's a very well-known result called Fermat's little theorem. And it says a to the p minus 1. P is a prime. A to the p minus 1 is congruent to 1 mod p, modulo p. This very famous result. You can also, you have to assume here that p and a are relatively prime, or a is not a multiple of p, I guess. Whoops, I need to fit a p in there. That's a mod p, folks. Sorry about that. So mod p, and that the assumption is that a and p have no common factors. Okay, some people I think write it as a does not divide p, or p does not divide a. I mean, okay. So that's the case here. That's what we have going on right here, because 2 and 11 are certainly relatively prime, right? So here it would be played by the role of 2 and 11, right? Okay, and so what we know right here is we can just replace this part with 1, right? So we know that p minus 1 is 10, so we know that 2 to the 10th is congruent to 1, and that's where you get this massive reduction here. 2 to the 10th is congruent to 1 by Fermat's little theorem. And it's conveniently called FLT. Not fun-loving turkeys, but Fermat's last theorem. Okay? So you see that's what happens here. So right here we actually just get that this is 11, right? This part is just 1. So this entire part right here would be 11 but 11 is certainly congruent to 0 mod 11 trivially, right? And so we've this whole part right here, 9 times 1 plus 2 is equal to 11, but 11 is 0 mod 11. So we've proved what we set out to prove, QED. QED, the proof is complete, quite easily done, not quite easy, I guess. All right, so finished our proof. Now, y'all, I know there's some souls out there who go, okay, that's 2 to the 76 is an awful, excuse me, let's just go down and do an example here. Notice right here, remember our condition. Our condition, any number that's congruent to 6 mod 10 is going to get the job done right here. And 76 is one of those numbers, right? So 76 is congruent to 6. And this is just an example, okay? Because, again, the numbers are so large, you can't do it by hand. I used, I think, Wolfram or one of the online things. Okay, but mod 10. Again, 76 is equal to 7 times 10 plus 6, so it certainly meets the initial condition that was required for this proof. And again, this is just a concrete example, so you see 76. Remember, we needed this. We needed n congruent to 6 mod 10 in order for this statement to hold. Okay, n congruent to 6 mod 10, and that's what we have right here. 76 is congruent to 6 mod 10. And this, look how big, you got this large, unpronounceable number right here. 2 to the 76 plus 2 divided by 11 yields an integer. Okay, so anyway, that's just a concrete example. But anyway, we finished the proof basically right here when we observed that Fermat's little theorem turns 2 to the 10th into 1. Okay, this little 2 to the 10th is 1 because 11 minus 1 is 10 right here, right? Okay, y'all, that's all. Hope you enjoy.